Hello, everybody. Welcome. So let's go ahead and get started. It's my honor to introduce Michael Posa. He's an assistant professor at UPenn. He runs the DARE lab, part of the GRASP lab. He's a recipient of quite a few awards and funding, so he's clearly qualified to do this robotic stuff. He did his undergrad at Stanford, PhD at MIT with Russ Tedrick, some of you may know, and also spent some time as an engineer at Beckman Robotics, so if you have a chance to chat with him, you can bug him about industry too. The key highlights, I think the really exciting parts here for this talk will be about contact-rich manipulation. So if you're interested in how to make and break contact, how a robot interacts with its world in a physical way, this is the expert that we've invited to satisfy those questions. Without further ado.
All right, thank you so much for the introduction. And it's exciting to be here. I was here last week for Coral, and I think as you'll see, some of the talk today has really been informed by some of my takeaways from that conference. So you'll forgive me if in the middle I sort of get on a soapbox a little bit and talk. Okay, so before I start, I do want to acknowledge our fantastic students in the lab who've done this work, some of which who have recently graduated, so I'm excited that I now have graduated PhD students, some of which who are going to be looking for PhDs in the coming year, so I'll try to flag them as well. Okay, so, most of us, or maybe even all of us in this room are roboticists, right? We've seen things like this, okay? We've seen Atlas doing super exciting dynamic behaviors, running, jumping, throwing toolbacks. We've seen, deep learning applied to dexterous manipulation. And I think it's important to have that excitement, to feel this sort of rush of where the field is going, and I don't want to take away from that. But at the same time, right, these videos aren't even all that new anymore, certainly not the OpenAI hand. And I don't have an Atlas in my house yet, or my workplace. Okay, so maybe I do, because I'm a roboticist. In my workplace, I do, okay. But I don't in my house, and I don't have a dexterous hand either, or a shadow hand or something like that. What do I have in my house? I have a vacuum cleaner. And what happened to the promise of the field? We've been promising these extremely capable, high-performance machines for quite a long time now. And it feels like we're still pretty far away, right? So what's missing? Okay, and what are we going to do about it? And to be a little more specific, I think one thing that's missing is the ability to deal with generality, to deal with the unknown. I would like to work towards a robot that can enter an environment, hopefully not one quite as chaotic as this person's garage, but an environment that is filled with things it's never quite seen before, where it's going to have to accomplish a task that's different from anything it's done before. It can leverage past experiences, sure, but there's something new about this setting, and I'd like to go from this into some kind of task completion within a few minutes. I think it's a reasonable goal. I think humans can do that. I think we're fair in asking our robots to handle the unknown with some degree of skill. And you can also imagine, well, if I want to go into a setting like this and accomplish a task, there's a lot of things that I'm going to need to deal with. I'm going to need to be able to find where the tools are and then manipulate them. And those tools may be a little bit different from what I've seen before. And I'm going to need to be able to pick up and work with the pieces of wood and align them in certain ways. Maybe there's some peg insertion bits that go along here. There's some forceful interaction with the tools. I also am going to need to make sure I protect my environment so I don't damage it. You can see this person's laid out cardboard. So there's a lot of bits and pieces for us as roboticists to work on. Obviously, I'm not going to talk about all of them today, but I do think this idea of dealing with novelty and in dealing with low data is going to be relevant. Okay. Now, I think, okay, again, very much informed, right, by what we saw at Coral. And I'm sure many of you here were at Coral recently. Why do I care about low data? I think there's a perspective that's to say that data is all we need, and we should be putting our efforts towards scaling data. And we've seen this, for example, from the recent OpenX announcement, where Google and many collaborators collected basically as much data as they could. So something like 20 different institutions, 22 robots, 500 skills, 150,000 tasks and 1 million different episodes. So lots of data has been collected, and they're trying to see sort of what they can do with this. I think this is interesting. I think this is an exciting direction for the field to take. At the same time, this type of performance has really only scaled to pretty simple tasks at this point. Right? We'll see where it goes in the future. Again, I don't want to discount it, but I think we're a far cry from saying that data has solved all of robotics. We can also look to other fields. Okay, look at to press clippings from other areas, and ChatGPT. Okay, again, very, very exciting. Again, we'd be foolish to ignore this. But ChatGPT is not quite reliable enough where you would trust it with your life, right? And I think that's something we're ultimately going to ask of our robots, that they be extremely trustworthy. So, what are we going to need more than data? And obviously, a lot of work now is going into trying to fix this on the LLM side. If you think data is all you need, you could also go ahead and look at the autonomous driving sector, right? Where Tesla has had the ability to collect vast amounts of data for years now from all of their cars, and yet autopilot is not particularly safe at this point in time. So what's missing? Again, is it just more data, or is there something more fundamental? Okay, we can look at Cruise as well, where the autonomous vehicles continue after decades of research to still require significant amounts of human intervention. I would also say, and this is something maybe you disagree with me, but I would say that these problems are probably easier than our robotics problems. Right? The level of environmental complexity in autonomous driving is probably simpler than what a in-home robot is going to have to encounter. So I think we should be asking ourselves, well, how much data would we realistically need to collect, and is that possible? Okay. I'm not going to suggest an answer to this question, but I think it's one we should be trying to understand. I know Google has an answer. Right? You can talk to people at Google, and they'll give you an answer that's sort of along the lines of the kind of data Tesla's collecting. But I'm not sure I believe it. And I think even if you believe this, right, that this is possible or likely, it's not necessarily the right question for academia to answer. And this is where I'll take my soapbox for a minute. We should be seeking out problems where we can have impact, right? Where our unique skills, our insights are going to be driving the field forward, pushing that boundary of knowledge forward. I think if you're asking yourself, well, I just need to collect more data and that's going to solve all of our problems in robotics, then someone like Google, someone like Facebook is going to do it. Okay? And there's not necessarily a role for PhD students and professors to play. So I think it's important to say, okay, well, maybe this is not the case, right? And we should be asking slightly different questions. Okay. On a more philosophical perspective, right, if you are going to buy into this big data as a solution, you should also be asking who's going to own the data and who's going to own the trained model. We can even already see that, right, with RTX, where the data is public, okay, thankfully. Lots of universities contributed to it, but the trained model is not. Right? So that, I think, is a direction we're going to continue to see industry pushing forward. And so, again, is data the answer, and if not, what should we do about it? Okay. So I'm going to leave that aside and move on to the more technical bits of the talk now, and really sort of focus on this question of, do we need all this data? And if we do, and if we don't, well, why? Or why does it seem like we do? Maybe is the right way to put it. And I'll leave data collection to others. Okay. So I'm going to try to sort of cover 3 points here today. And as I get started, I should say, please feel free to interrupt, right? Or argue, or disagree, or ask questions, right? I'm happy to stop and discuss and skip some slides if that's what it comes to. I'd rather have a conversation if possible. Okay, so we'll do 2 things. First, I'm going to try to argue that deep learning, or learning in general, is biased, inevitably, and that those biases by quote-unquote default are misaligned with contact, misaligned with making and breaking contact with the environment. And that this misalignment is what drives this extreme need for large data that we currently see. I'll try to solve that problem. So I'll also talk about steps we've taken towards addressing that issue, both in terms of deep learning as well as more simple representations. And then I'll also talk about model-based control. So how do we use these learned models for control? To start thinking about that first question, I'm going to show this figure here. This is from a paper by Rika Antonova at Stanford and colleagues. And they were looking at this differentiable simulation problem. So they had a simulator, they collected some data, and they were trying to learn a model and basically backprop through the simulation. And this was a pretty simple problem. They had really two things they were trying to learn. Some sort of rotation, some angle offsets essentially, and this was a couple of flippers that are interacting in the ball. And the loss landscape for this problem is absolutely horrendous. You can see this cartoon right here. This is drawn. You have these really big flat regions where you have no gradient or zero gradient. And you have very, very steep, narrow valleys. You have local minima all over the place. And if any of you have played with differentiable simulation and trying to scale it, I think you immediately run into stuff like this where it doesn't scale. What's happening here? What's happening here is that the underlying physics are extremely stiff, and your simulator is exposing those underlying physics and trying to optimize through them, and it's failing. So for the first part of the talk, we're going to look at data that looks something like this. So we've collected some data. This is an object moving. Here's its trace in SE3 over time. And I think most people in the room know what's happening here. You have a pretty good sense for what this is. There's an object. It looks like it's falling. It looks like it hits something right around here. And then it looks like it bounces. And then maybe hits it again, maybe here-ish. And then maybe a third time, maybe more. And then at the end, it's sort of sliding and coming to stop, to rest. Okay? We have an intuition built up for what's happening here. And I show this because I think understanding this is not an impossible problem. Right? This is not even that hard of a problem for humans to understand. Right? We don't, from this video, know exactly what this object is, but we have some sense that it's hitting something that's kind of flat. In fact, that data comes from a cube. And then we took a cube, and we asked our robot to throw it a bunch, and we collected data. We collected hundreds of tosses. And then we could ask a neural network, either an MLP or an RNN, to fit that data in a single-step fashion and then roll out predictions. And what you see from our best attempts, this is hundreds of tosses, which I think should be enough, is that it gets the bulk motion more or less correct, but it really struggles with orientation. It really struggles with things like penetration. Right? And this is because it has no understanding of this impact effect. Okay. Fundamentally, what's going on here is that when we train a neural network and we introduce something like weight regularization, we are now biasing towards smoothness or biasing towards low Lipschitz functions. And the phenomenon we're trying to capture here, this robot interacting with the world, object interacting with object, is not smooth, it's not simple, it's not low Lipschitz. And so we have this basic misalignment. Implicit learning is one step in this direction. I think in implicit learning, and by implicit learning, I'll take a simple perspective here, one variation, which is say, I'm going to learn, instead of learning some function y equals f of x, I'm going to learn some function h of x where y is the argmin now of h of x comma y. This is one variant on implicit learning. There's lots of others. And what we've seen is this is really useful for representing non-smooth functions. We've seen this, for example, in things like energy-based learning. We've seen this in diffusion policies and in diffusion models and in implicit behavior cloning. This implicit function can represent things like discontinuity quite nicely. And so I think it's one important piece of the puzzle. Differential simulation is another variant in this idea. So I want to make sure that when I talk about implicit learning, I'm sort of putting all these things into the same bucket. So differentiable simulation says something like, learn some parameters for my dynamics, geometry, friction, inertia, maybe even a deep network for residuals, and then take those parameters and pass them into some kind of physics engine, some kind of convex solver. This can be whatever your favorite simulator is. It can be Joko. I don't care. Right. And so this is essentially an implicit model, right? These parameters imply the dynamics, imply the motion. Via simulation, but it's a very structured one. Okay, and so what I'm going to try to argue, and I haven't sort of made that point yet, but I'm going to try to get there, is that this representation is important, but it is not the only answer. Okay. This implicit representation is part of the solution, but it's not the only answer. Simply representing the thing we want to learn is not good enough. We actually have to think a little bit more deeply. So here's a toy problem I want to use. So imagine we took a point mass and we just dropped it on a table. Okay? When it hits the table, it stops. That's the model. And we're going to do this as simply as possible, where we're only going to try to learn the height of the table. So the only thing we want to learn is this height, call that the ZG or theta. And we're going to generate a loss. It looks like, well, I take my model and I parameterize by theta, and I evaluate it on my data, and I compare that with what I've observed. This x to x prime transition. And what you see here is that, well, if I underpredict the height of the table, then my data, which stopped at the real table, never actually hits my predicted table. and therefore it never predicts contact, and therefore the gradient of the loss is 0. We have a very flat loss landscape. That's this on the left here. And then on the right, we would say, well, I overpredicted the height of the table, and I have penetration now in my data. And so whatever simulator I'm going to try to use is going to try to eject that object out of the surface, and I'm going to get this very stiff response. And so this is that cartoon version of that plot we saw from the paper by Antonova, where this is a horrible loss landscape to work with. Now, I think the prevailing wisdom at the moment is to say, well, that's an issue, but let's just smoothen everything out a little bit. Let's relax our contact model. Let's make it a little bit softer. And if you do that, you get something like this. So this is a Mujoko model that I've cartooned up for this problem, where it does a nice job of generating gradients in large chunks of the parameter space. In this case, by allowing some contact when there's penetration and sort of dealing with the before there's contact, allowing forces before there's contact, and then dealing with penetration a little bit better. And this is a nice answer, but there's a couple of issues here. So one is we can already see that for this particular contact model, we still have this flat region. That's not inevitable. I don't want to claim it is. I mean, there's other contact models that would kind of round this corner out too. Of course, you're still looking at, if not 0 gradients, almost 0 gradients, and so maybe that's not helpful, but it's something. But the bigger issue here is that we've actually changed the answer now. We've caused this shift, we've caused this bias in the solution now, where by softening our contact model, we've introduced fundamental error in the model we're learning. This is just a toy problem. This is the simplest version of it. But this trade-off, if you just use a soft contact model, is actually inevitable now. You can make your learning problem easier by relaxing your dynamics, right? But then you get the wrong answer. And again, maybe there's things like homotopy-esque methods you could try to work around this issue, but it is pretty fundamental. And a point I want to make here is that it's not inevitable. This is not a trade-off we are forced to make. It is a trade-off we have to make if we're in this paradigm of saying, use your model for prediction. Right? Because my model is stiff, therefore the prediction is stiff, therefore my loss looks stiff. So if you follow this step of saying, use your model for prediction for loss, you will end up here to some extent. But you don't have to. Again, we can get something that looks like this green curve as our loss landscape. This is our implicit loss that I'll talk about a little bit later. So that's where we're going. We want to have our cake and eat it too. We want to get the right answer with a nice loss landscape. Okay. Before talking about the answer, I want to sort of highlight some of the work we've done on trying to understand this problem. I think that's perspective we often take in my lab is trying to distill things down to their most basic element, try to understand that basic element, and then scale up from there. So we ran a couple studies. One was just a pure empirical study, right? Take Mujoko, take a cube, simulate the cube in Mujoko, and vary the ground stiffness, vary the contact stiffness, and we have a soft, medium, hard version here, where the hard is the data in blue, the medium is in yellow, and the soft is in red. The video here is the medium version, so you can imagine soft being very unrealistic and bouncy, and hard being kind of more what you'd expect from a rigid cube. And what we see time and time again through this process is that the stiff model is hard to learn. This is not a surprise, right? This is not a shock, right? I have a stiff ODE, I'm trying to optimize with respect to it, and the learning runs into trouble. It runs into trouble both in terms of generalization, so whatever you learn fails to generalize, and also in terms of training, that your training error actually is hard. It's actually even just hard to memorize this data that comes from the stiff system. We also looked at trying to generate bounds for generalization. This is work that was at L4DC a couple years ago. And for this, I think it's useful to just take a step back and ask, what do we mean by a loss? What is our loss trying to do here? I think it's easy to kind of skip that step and just pull whatever people have used from the most recent paper. And so if I'm asking this question of I have some model, some f of theta, f of x over here, and I'm trying to understand how well does my data match my model? That's sort of the basic question here. Well, if I assume that my inputs and my outputs both have noise, have Gaussian noise, let's say, then the quote-unquote correct answer from a max likelihood perspective is to minimize graph distance. So my loss should look something like my distance to the curve. Now, graph distance, of course, is not easy to calculate. All right? It has to ask, is this embedded optimization problem. Find this point x hat on the, in the x direction such that you're closest to the curve. This is not particularly tractable, but it is probably the right answer. There's errors in variables. Okay. Prediction error, on the other hand, is much more tractable, and this is why people use it. And they say, forget about optimizing over x hat. Just pick x hat to be equal to your data point. Whatever you've assumed that the input is correct, and just look at variability in the output. Okay. And then you get this vertical distance, and it's easy to calculate. There's no optimization problem. And these things are the same up to a Lipschitz constant, right? If the function I'm trying to learn is low Lipschitz, these are functionally equivalent, and we don't care so much about the distinction between the two. But, okay, and you can imagine where this is going. If my function is stiff, if it's high Lipschitz, well, this data point over here could have very easily been generated from my curve, just with a little bit of uncertainty or noise in the x direction, except my prediction error is very big. And so my loss, I would say here, is not capturing what I want, right? And then you can try to apply some standard techniques from generalization theory and say, well, if the loss function has a high Lipschitz constant with respect to my parameterization, then it's going to generalize poorly. At least it might generalize poorly. Whereas if I have a low Lipschitz constant, things will generalize better. So we're in this business of trying to find lower Lipschitz loss functions. Okay. One other perspective. This is sort of like the simulation perspective. I think the first time I presented this way, so hopefully it's clear. We could think about simulation as an optimization problem. I think this is sort of an underpinning concept behind any simulator you're using right now. Okay. Whether or not they're solving it as optimization problem depends on the simulator, but they're all conceptualizing it this way. And so a purely rigid simulator is going to say, find a contact force lambda that satisfies some rigidity constraints, some complementarity constraints. I could take the simulator and I could put it into my learning problem, my loss problem, and say, well, think about my loss now as saying, compare the difference between x prime and my f of x comma lambda, that's my dynamics, where lambda is a function of x and satisfies my constraints. This is sort of the normal thing. You could do Majoko now, or Dojo, or any kind of relaxation, Drake, whatever. And instead of this hard, rigid constraint, you'd have some relaxation of it. And then, again, every simulator has a slightly different relaxation, but they can all be thought of in this perspective. And my loss now looks the same. It says lambda is a function of x, and it approximately satisfies my constraint, whatever that means. Okay. There's actually another interpretation of these relaxed models that I think is useful, which is that the force here dissipates energy maximally. So it's the maximally dissipating force. So it's actually the argument to some optimization problem. So you can think of this as an energy-like function or a power dissipation-like function. So lambda is now the argument of this function, and we can do the same thing. Okay, so lambda is now the argument of some dissipation function, again, depending on x. And all of these things, these three ideas, are all going to basically lead you to the blue, very, very stiff line, or the orange line where we're changing the answer. What we're doing here is a little bit different. We are going to not simulate. So however you want to embed your model into your simulation step, I don't really care. Okay, it can be the relaxed version, it can be the rigid version, it doesn't matter. That's for you to decide after you learn the model. But we're going to write down a different loss function. And that loss function is going to look a little bit like this energy minimization problem, except we're going to take this constraint that lambda is the argument, and we're going to sort of just lift it up into the optimization problem. So we're going to say minimize lambda with these type of terms here, and I'll get into what exactly that means in a second. A couple of properties. First is one is this better approximates things like errors in parameters. It better approximates things like graph distance rather than using foreign simulation. And fundamentally what's going on here is that our force now depends on x prime. Because we're not simulating, we can do something like inverse dynamics, where we're saying given x and x prime and a model, what's a good force that goes along with that? And the neat thing here is that all of these simulators involve some sort of optimization problem, and so does our loss. But our optimization problem is actually easier than simulation. Right? In the supervised learning paradigm, we don't have to simulate. There's a couple ways to interpret what's going on here. I'll give the physics version first and then the learning version second. So the physics version says is that our loss here hypothesizes forces. So it's observed some motion. Maybe this, in the case of the ball drop, that the ball stopped very suddenly. So observe that fact. And it then has to infer what caused it to stop suddenly. And so it's encouraged to pick a force that generates that stopping motion. That's our first term in our loss. And the second term in the loss says the force should also be encouraged to match the model. And the result of this is that in the training process, right, because you're not simulating, you're generating useful gradients essentially everywhere that correspond to either fixing the model or fixing the force. The more learning-based perspective, okay, I guess before I say that, the other thing to add here is this is fundamentally not a soft contact model. It is a relaxation of the constraints, yes, in the same way that a soft contact model relaxes constraints, but it does so with its dependency on the next state. And I think this is the takeaway here, right, is that in this supervised learning paradigm, if you're trying to learn something that is very stiff or is non-smooth, don't just think of this as an input to output mapping, particularly if you have this implicit representation. Right? You can better engineer loss functions that work well away from the true global minimum. Okay. The more learning-based perspective is essentially to think of lambda as a slack variable. So we've lifted up the learning problem, we've introduced some slack variable. And we've paired that slack variable with an energy-like function, and then lambda we're going to say is the minimizer to that function. In the sort of pure energy learning perspective here, inference becomes the sort of classically hard problem that you have to deal with. You have to do some kind of sampling, MCMC type sampling to perform inference. Because in this domain we are leveraging some physical structures, it actually makes inference feasible. So I think you can think of this as energy-like minimization, but it's actually one that's tractable. Okay. The result of this, and I think this is the exciting bit, is that we have very data-efficient model learning now. We can take our cube tossing data and we can extract the model, and that model learns geometry, as you see up here, almost instantaneously after a handful of tosses. And it learns things like friction, it learns things like deep neural networks as residual dynamics, it learns a deep neural network that describes geometry. So maybe one point here is that this paradigm works really nicely for low-dimensional learning. Learn a few parameters, widths and heights and masses and so on. But it also works quite well if you want to do deep learning. Okay? And it works because it's aligning biases of the problem with the biases of the data. And so we see, essentially, for this cube example, in tens of tosses, we pretty much nail the predictive model. Deep network takes a lot of data and continues to require, is orders of magnitude more data. And differential simulation in red really just kind of bombs out. Depending on your initialization, it might just fail. Okay. Most recently, when we presented this at Coral this year, we've taken the same idea and tried to scale it up a little bit. So we've included an articulated object, and we've explicitly tried to learn residual dynamics as a deep network or as an inertial parameterization, and as well as the contact parts. And the really cool thing here is that because we bias everything we learn towards smoothness, that's automatic, right, by weight regularization. We actually can disambiguate the two. So the non-contact force is biased towards smoothness, and the implicit representation of the contact bit also biased towards smoothness. And so you can actually learn here without any human supervision, without any annotation of when contact occurs, without any explicit detection of contact. You can learn which motion, because it was stiff, because it was high lift shift, must have been generated from contact, and which bits of the motion were probably generated from some non-contact effect. Any questions on any of the learning bits? I'm going to transition a little bit. Yeah.
Do you anticipate this generalizing with some shenanigans towards like soft or deformable objects as well?
I do. Yeah, I do. I mean, soft and deformable is both easier and harder. So I think it's easier in the sense that you no longer have impacts. You do still have non-differentiability because the object doesn't move until you touch it. So you have this non-smooth transition when you make and break contact, but the actual physics are not quite as stiff. So it's easier in that sense, but obviously harder in the sense that you have this very deformable object. What is state? Those fundamental questions. I think we've thought about things like using key point-based methods to deal with softness, or maybe using kind of a deformation-based approach where you learn deformation. If you've seen like the work from Yuma Fazeli on the topic, things like that, I think could apply here. Okay. All right, so we can learn these models, and we can learn them quickly. And we can learn them in a data-efficient manner. So I'll talk a little bit about control. What do we do with the learned model? and the story for this is I would like a controller that is going to, in real time, autonomously, by itself, decide what to touch, where to touch it, and when to touch it. It's going to make these hybrid control decisions in real time. And so how is it going to do that? It's going to have to evaluate all possible combinations, and it's going to get stuck. This is a problem I've been working on for a number of years, really since basically year 2 of my PhD, and I'm super excited that Alp Identiglue led efforts here and got us moving. If I think about control, right, the first thing I would teach or try is something based on linearization. And linearization fundamentally can only really approximate a single context. Right? If I linearize motion in the air, it tells me really nothing about what happens when I touch the table. And therefore, things like IOQR can really struggle to explore contact modes. Even if I use differentiable simulation, I can write that down, I can code it up, it'll work, it'll do gradient descent correctly, but it may not uncover the fact that I need to reach out and touch the wall to prevent falling, or I need to touch the object to make sure it moves. So rather than linearization, we're going to use what I think is sort of the simplest next thing, which is the idea of a linear complementarity system. So this is a linear system, except it has this complementarity constraint, and this constraint down here encodes the multimodal behavior. This is essentially a local approximation of what your simulator does. What we're doing essentially is we're taking all the different bits of your model that can be linearized, and we're going to linearize those. Everything that's differentiable. Geometry, non-contact motion, etc. Jacobians, we'll linearize all those. But we'll leave the multimodality. So if you take this as your model, and you embed it into an MPC framework, you get a QP with complementarity constraints. This is a QP with non-convex quadratic constraints. You could equivalently think of this as an MIQP. This is not tractable, okay? At least not right now. And I would hazard that it's not likely to become tractable in the near future to solve this to global optimality. Okay. So we're going to be stuck now with the local method. I think we have to accept that fact and just live with it. And if you're stuck with a local method, I think it's also important to think about what do you want out of your algorithm. Okay, so what do I want? I want it to be fast. I want it to run real time. I want it to not get stuck in whatever the current mode is or whatever the current plan mode is. So it should be capable of exploring, in some sense, options for what to touch. And if it can do those two things, I'm going to be pretty happy with it. Okay. Our approach here, which we're calling C3 for consensus complementarity control, is essentially ADMM. It's ADMM with two stages. One is which we ignore the non-convex parts. We ignore the complementarity constraints, and we just solve a QP. And in the second stage, we project back onto those non-convex constraints. Okay, so this stage 2 is the hard part. The nice thing here is that it turns out this projection operation, which is the difficult bit, is actually separable in time. So you end up with a prediction horizon of n. You end up with n separate predictions in time, and so this can be decomposed nicely, and then you bring them back together via consensus formulation. This prediction horizon, I think, is actually really important, right? In many ways, modern control has moved towards these very myopic, kind of instantaneous-like control policies. But instantaneous control is not useful in this case. If I want my controller to uncover that I have to touch something, then the prediction horizon has to be long enough to where I touch it. Okay? Local perspectives are not good enough, so we need this big prediction horizon. So I think this scaling is pretty critical. Okay. The result of this is that we can now run this at something like 30 to 100 hertz for a prediction horizon of 5 to 10 for some pretty interesting problems. So we can roll balls on a surface. We've done this with 1 or 2 or 3 balls where we've given it simply the objective of saying, make the ball move, follow a path. Okay? The rest of it essentially is figured out by the controller. It decides what to touch, where to touch, when to touch it. It can do this even if it has to corral multiple objects following a particular path. So this I'm super excited by. I think we're still in the process of scaling this up and thinking about how to make these projection operations faster and how to scale them to more dexterous behaviors. But that's work in progress. It does have one flaw, though. And like any good model-based controller, it's very sensitive to the model. And in particular, it's sensitive to whether or not it actually touches the object as it expects. Right? If it has a poor understanding of when it's going to touch the object, it's either going to miss it like here, or it's going to jam into it and risk damage. And so there's this sensitivity, and there's this particular sensitivity to the hybrid aspect of the problem. So this is work, I would say, first of all, led by Wei-Cheng Huang, who's a master's student in my lab and is looking for a PhD program, so keep an eye out. He'll definitely be applying here. Submitted this to ICRA. And so the idea here is to take the model learning parts we've done and combine them in an adaptive fashion. And unlike most adaptive controllers, we're explicitly going to try to adapt the hybrid aspect. So we're going to try to online learn more or less the hybrid guard when we make and break contact. And we're going to do that from in this residual learning framework. And so you can do this, run this residual learner. And the really cool thing here is that because we have this implicit loss function that generates meaningful gradients essentially everywhere, we get a nice gradient simply from trying to touch the object. If you try to touch the object and fail, you actually get a useful gradient that says, okay, you weren't quite close enough, you should get closer. And so there's this initial phase where we're even failing to touch it, we're still learning something, and then it pretty quickly adapts and becomes more and more successful over time. So it works for a sphere with a poor initial model. It works pretty reliably in this case. And then, because I'm a cruel advisor, I said, try some other things, try some fruit. And those are kind of like balls, and they should kind of work. And so it turns out they do. You can get an orange to roll, or you can get a lime to roll. It's a little bit trickier because these things aren't quite round. And so if you make a mistake, or even if you don't make a mistake, sometimes they just roll away from you, like they topple and kind of tumble away. But the same process actually works surprisingly well for almost round objects. And this is a very, very simple paradigm. We're just doing an online adaptation of that hybrid guard and otherwise considering the object to be a sphere. Okay, so I think we've made some nice progress on how to learn from data, and we've made some nice progress on control. But robotics, and we're to blame for this. We've been promising science fiction, right, for decades, okay? And in all honesty, rolling a ball on a table is not the promise, right? We're hoping for something better than that, right? We're really operating in these more complex environments. And I think it's still very much an open question as to how we're going to get there. Right? What is the key that's going to unlock, moving from very structured tasks? I say this even for something like imitation learning or behavior coding or these more model-based approaches. What is going to get us to generality? And so for this, I want to sort of think about how we as humans approach these problems or how we think about these problems. I think one underlying question is, well, I can do control, I can learn models, but I'm not going to model the whole world. I'm not going to model my kitchen. I'm not going to model every object in it. I'm not going to model what happens if I start banging all those pots and pans together. There's things I simply don't care about, and there's things that are relevant. And how do we disambiguate between the two? I think this is a really sort of key question that we as a field are starting to think about. To be more specific, let's think about an in-hand manipulation problem. So even if I want to take something like my phone and start playing with it, okay? Well, the contact between my hand and the phone is pretty rich, right? It's occurring in lots of different places. There's lots of different combinations of contact that could occur or even are occurring. And if I say there's maybe 10 possible contacts, now there's 2 to the 10 possible modes, that's 1,000, but maybe there's more like 10,000 or a million or something like that. It's not a useful way to think about this problem. It's not necessary, right? I would say even this task, which I think robots can't do, okay? They're getting close, but they can't quite do this. Even this task is not that hard, but it is multimodal. And I sort of want to think about this very carefully. Like, these problems are hybrid. They have mode switches. But the number of modes that we need to think about, that we need to reason on, is not the same as the number of modes that are actually in the physical system. So I would say philosophically, I think a controller can be successful while only reasoning over a few modes. Which is to say, many of these other modes, maybe they're so suboptimal that they don't matter, that we can just safely ignore them, right? Yeah, I could drum my fingers on the phone, but I don't need to. It's irrelevant for the task. Okay? Maybe some of these modes only occur very ephemerally. Okay, so I could have my ring finger on it and not my middle finger, but that's only going to last for only a few milliseconds, so I guess I can safely ignore that. Or maybe they just look like nearby modes, and so they don't really matter all that much. Right? There's lots of reasons we could safely ignore things, but I think we can. Right? Empirically, we certainly can. And so what does our problem setup looks like is that we're going to say there's some true dynamical system, and maybe it's high dimensional, it has lots of context and lots of modes, maybe it's nonlinear and so on. And we're just going to say, let's approximate that with a linear complementary system. And let's force that linear complementary system to only have a few modes. What can we do with this? Right. We'd like to do this in a task-driven manner. So we'd like to learn this simple model, this simplified model, in a way that explicitly enables high-performance control. Again, I don't necessarily care that it matches my data everywhere, because that's not what I'm interested in. I want high performance back. So I want something that's going to achieve high performance. And we've taken, I think, so far the simplest possible approach here. Okay, so this is really very much a first pass at this question. And this is going to say we're going to collect some data. We're going to learn a model using the model learning bits that I talked about already. We're going to use that model on policy for control using the control bits we've talked about. We're going to collect more data, and we're just going to repeat that in a loop. Again, nothing fancy going on here. It's sort of on policy model learning. And despite the simplicity of this approach, it's actually shockingly effective, at least in simulation so far. So we can learn things like this in planar manipulation with 3 fingers of an object in, let's say, 3 to 5 minutes of data. Okay? No prior information about the object, about the goal. This is essentially a reinforcement learning problem where we've just imposed this LCS structure on the learning problem. Right? Even though we train it without any domain randomization, it's actually surprisingly robust to disturbances. So these are increasing difficulty of disturbances over here. The cool thing here, I think, is that even though we have this simple model, it's actually effective over a pretty wide range of tasks, and the policy that emerges is in fact multimodal. So we're capturing something fundamental about the problem in this data efficient manner. We also applied this to synthetic problems, I think, to sort of better understand the reduction that's going on here. And so these are systems that originally were linear complementarity, and we're just trying to crush the dimension of the modes down. And what you see consistently is that even if you have a system that's colored here by the different modes, has lots of modes in it, we can actually approximate it very quickly with relatively few modes, in this case 4 modes, and we get basically the same performance back. Okay, so we see over basically random systems essentially an order of magnitude of reduction with only a 1% cost increase. So we can generate random multimodal systems, we can simulate them, evaluate them, run MPC on them, and it turns out we didn't need that many modes to achieve high performance. So this works pretty well. It's data efficient, it pairs nicely with the control policy, but it's not optimal asymptotically. Performance stalls out relatively quickly here. And this comes from the fact that we're just doing model learning. Right? We're trying to learn a model, and we're using that for control. And that process, while it's collected on policy, still doesn't quite understand that control performance is the ultimate objective. And again, we're taking baby steps in this direction. And so, to try to address this, first I want to understand what is the problem here, right? Does this fail because the model is not rich enough? Does it fail because of something else? And so for now, we're going to stick with the LCS and just try to say, given this model representation, how far can we push it before we add complexity? And so again, a simple strategy, right? The learning strategy here is quite straightforward. We'll call this LCS RL. We're basically just going to fine-tune reinforcement learning. So we're going to parameterize our policy via the model itself, run model-based control, but we're going to use PPO to optimize the model. And we're going to do this only for fine-tuning. We're not going to do this from scratch. We're going to learn a model from data first, and then we'll fine-tune with reinforcement learning. And I think the results here are not surprising, but I think they are worth keeping in mind. So the results here essentially say, if you just train a model, that's the thing in blue, then you get really good low data performance, but then it sort of falls off as it maybe overfits to model matching and not so much control. If you run something like deepRL, that's in yellow, or even PPO only learning the model without the initial model training, without the initial model training stage, or just using PPO, it really struggles to scale. Okay, not a shock there, right? It's going to require lots of data. If you do some kind of model-based RL with deep learning, this is the Nagamani paper, that also struggles to scale. And then, okay, if you do RL fine-tuning, you actually see, continued improvement in performance, as you might imagine from sticking with the simple model. So this is not a shock, but I think it is informative. And then I think one of the neat side effects here is because all objects are cubes, we can just use this to fine-tune. So we could say, well, let's start with the cube and apply it to another system and just fine-tune from there. And so you can try a mug or a wrench or a bunch of standard objects, a clamp and a banana. And success rate is not perfect, but it's shockingly good for 6 minutes of data, for almost very, very minimal data here applied to these tasks. And so how far, basically, these are definitely not linear complementary systems, right? There's nothing linear about these models, but you can actually get pretty close. And I think this raises some interesting questions, right? Which is how do you take good but not perfect low data performance and then continue to scale that as you collect data and get into the more high data regimes. But the ability to go from nothing to sort of working very, very quickly, I think is quite useful. Okay. And then lastly, this is a bit of a change of pace. We've been thinking a lot in my lab about how to start bringing vision into the picture, because I think it's critical to be reasoning about real sensors and moving away from things like motion capture. And then once you start bringing in vision, I think you want to also ask yourself, right, what are the right questions to be asking? Right? What should we ask for? And going along with the theme of the talk, I think if you think about these tasks here, right, even a human description of what's going on is very much driven by interaction, right? In this picture, the robot holds a box of sugar. It uses that box of sugar to push the applesauce, and then the applesauce bumps into the shelf. Right? Every bit of that description was driven by when and where contact was occurring between different things in the scene. Same would be true for the bowl. And so we want to say, can we use vision to extract these relevant bits of information from the scene? We can all tell what's happening from the image. Can we ask a computer to do it? And I think it's useful by narrowing down the question here, okay? By specifically asking the learner to detect contact, as opposed to something like reconstruct all the geometry and then use that reconstruction to infer contact. I think by narrowing the question down, we can get more reliable answers. So the problem we want to ask here is, can we detect contact in novel scenes when holding novel objects? So this is extrinsic contact between the held object and the scene. Force sensing here might be useful to some extent, but because the force sensors aren't co-located at the contact event, they're only partially useful. So for now, we're going to ignore them, and then maybe in future, we'll try to bring them back in. To do this, we're going to try zero-shot sim-to-real transfer. So we're going to train this entirely in simulation, where we have privileged information as to where the contact is occurring. We can generate data, and we're going to do this with a depth camera only, just to enable that sim-to-real shot. And the results for this, I think, are pretty promising. So what's going on in these figures is the pink is the hand-annotated contact from real data. The blue and the green are essentially the predictions from the network. And the cool thing here is that it works pretty well across a range of contact configurations. So on the left, we have essentially a point contact that transitions to an edge contact. It also, you notice, it starts to predict contact between the box and the table, which actually doesn't quite occur in this frame. So it gets that wrong. It jumps the gun a little bit, but it gets the bulk idea of that transition to edge contact correctly. It also deals pretty well with things like sliding, stick-slip transitions, you can see over here, or even things like occluded contact on the back here, where the held object is only partially visible. The ability to handle occlusions is helped a little bit by the fact that we provide the network with a single image of the robot holding the object. And this gives it some ability to disambiguate what the held object is from the scene. So we provide that a little bit of bias, and it can extract that. And then thanks to the reviewers actually on this paper, this is also a Coral down the road. This actually generalizes surprisingly well to out of distribution settings. So this is a human now inserting a book into a bookshelf, and you see it's doing a passable job, I would say, at predicting contact, even though this thing has been trained entirely on robot data. And then also for soft objects. So we've trained on rigid objects, and it works reasonably well for soft objects. I think this is an interesting set of questions, but by no means complete. Leon in particular, and this is a collaboration with Dinesh and Jayaraman, we're thinking now about, if we can extract this information from the scene, And it needs to be improved a little bit, but I think it's on the right path. If we can extract this information from a scene, how can we use it, right? In many ways, because these tasks are so naturally described, or not so naturally driven by this interaction, maybe these bits of information provide nice nice supervision for something like human to robot transfer or any kind of imitation learning. So these are questions we're asking. Also, I should say, Yutron, also a master's student looking for PhD programs this year. Okay, and with that, I'll just conclude there. Going back to my soapbox, I suppose, I think there's a really critical role for us as academics to play in robotics, and I think this role is even more pronounced if there's more than data that's going to be necessary to enable robots of the future. I think it's possibly true that if data is all we need, we can just all quit now and let people go out and collect data, okay, and stop doing research. But I think if it's not the case, then there's a really critical role we need to play. And I also really encourage people, particularly the younger students in the audience, to find problems where you can have impact, to find problems where your insight is going to push that boundary of knowledge forward, right? As opposed to getting into a race with someone down the street or across the country to produce this result first. I would say if you're looking at a problem right now, and you can say with some degree of certainty that whether or not you work on it, someone is going to solve it in the next year, maybe pick a different problem, right? You're not necessary for that task, right? So find something where you're going to have a unique thing to say. Okay. Unfortunately, I didn't talk about our locomotion work. We do some running and some jumping. It's fun with our casting lab. I didn't talk about it today, but it, always exciting to have a casting. I know you guys have castings and digits here as well. I want to leave with this message that first off, we're still a long way away. Okay, I mean, don't be convinced by flashy demos right now that robotics is about to be solved. I think there's still a very long way to go to these things deploy in the home or in the workplace. And I also think there's really nothing standard about robotics. Okay, and if you take a tool off the shelf, that tool has some bias in it. Whether it's hybrid system theory or machine learning, it has some bias in it. And we need to make sure that the bias of the tool we're using is aligned with the bias of our problem. And if it's not, we need to make some adjustments along the way. There's some threads I didn't talk about today. I'd be happy to chat about offline. We're definitely interested in vision, as I mentioned. So we're looking hard at basically like how can we take sets of problems like this and actually do everything from vision. And I think there's really nice connections between vision and contact, because both of them are very much driven by geometry. And so I think it's a way to frame it as a joint problem that we're working on. I didn't talk about tactile sensing. I think that's obviously a critically important bit here. We've done a little bit with tactile sensing for feedback, but I think there's a lot more to do in that domain. We're looking at imitation learning, behavior cloning. I think drawing these connections to implicit learning by introducing this implicit loss, I think there's a potential for impact there where the learn policy or the clone policy has similar features as the model. And then also we're trying to escape this local linearity. I think that's a big limitation of some of the control work so far, is the idea of geometry being locally linear, and so how can we get around that and have some interesting ideas that are not quite ready to publish. And with that, I'll say my lab's recruiting students and postdocs. Penn is recruiting faculty, so apply, come join us. It's an awesome place to do robotics. And I'll thank you all for your attention. I'll be happy to take any more questions. Yeah, good question. So for so for the bit where we were learning dexterity in a few minutes, that was object always on the table. So no lifting. I think there's two reasons for that. One is actually asking the totally unstructured approach we have right now to lift didn't work very well. And the other thing I would say is picking up objects is pretty easy. So why should we use something learned from scratch if we just want to pick an object up? I don't think it's the right approach.
Thank you.
So the other question is more on the high level one. So I know the Majuto, they use soft content dynamics model, so which probably that's why we'll see a lot of cheating result in simulator. And that's people also try to solve this problem using domain recommendation because they just just assemble a lot of dynamics and then try to learn the more policy that can perform well for all the dynamics. Do you think this is also a promising way to do the sim to real transfer? Like one dynamics is not good, but we can assemble a lot of dynamics model and then try to find a policy based on that.
Yeah, so regarding things like demand minimization, I think it makes a lot of sense, right? I think one of the big success stories for things like reinforcement learning is the ability to handle uncertainty simply via sampling, and domain minimization is a big part of that. I think the question I would have, though, philosophically is, can you solve every problem like that, which essentially requires you to be able to pre-simulate your problem. So either you have to have a model, or you have to be able to simulate essentially every instantation of your problem. And I think that works really well for some domains. I think we've seen a lot of success, for example, in things like Lego locomotion, where the domains are relatively consistent enough or low dimensional enough where you can ask that question. But as you ask your robot to solve more and more tasks, where now the task space grows in dimension from, let's say, walk at a certain speed in a certain direction to who knows what, right, in terms of a longer range manipulation task, I'm not as convinced that that's going to be a winning strategy, or at least a complete strategy.
All right, thank you for this great talk. My question is about the linear complementarity system you're using with Auto. So it seems to have very impressive sample efficiency. But one thing you mentioned was you were not learning from scratch, and that you're fine-tuning a model that you were learning before. So in the plots that you were comparing with other methods, is the pre-training portion of the data accounted for?
So the pre-training is basically this first initial spike. So we switched right around here.
Got it. Okay, that makes sense. Thanks.
You talked a lot about learning contact models and these very stiff dynamics, and that's a very valid issue, and simulators of Mojako have that issue. But I'm also curious about how do you actually optimize contact models? And we've seen from a lot of recent research that optimizing through contact actually introduces bias in your gradients, which limit you to a non-optimal solution. So what are your thoughts on that?
Can you say what you mean? Is that from a control perspective or for the optimizing?
I think most from a controls perspective, when you have very stiff dynamics, first order gradients tend to have bias under a low number of samples.
Yeah. I think the short answer is that's why we're not doing gradient descent, right? So if you think of the MPC strategy we're applying, it's essentially a direct method as opposed to a shooting method. I don't know if these words make sense, but it's a direct method, not a shooting method. I think if you're going to run a shooting method, then you're going to do some kind of gradient or even second order approach, and you're going to get stuck with these very stiff responses to the hybrid switches. And I think that's where you see things like ILQR or DDP really struggle to do mode exploration. And so I think by formulating this as a direct problem, we can avoid that, where the early stages of the optimization process are allowed to hypothesize essentially forces that might be beneficial, even if the forward rollout would not predict those forces.
Thank you.
We have time for a couple more questions.
Yeah, this is very interesting. So in the last comment, the last bullet point on your last slide, you talked about the fact that you're using local linearizations in these methods. Do you have a sense of classes of problems where these local linearizations are probably particularly insufficient for what you're trying to do?
Yeah, that's a good question. So essentially, if I think about manipulating an object, what the local linearization is doing is it's approximating the geometry as a hyperplane, as a local hyperplane. And so if I want to reposition onto the other side of that object, for example, I need to push it towards myself. Well, linearization is not capable of that reasoning. And so, fundamentally, that's the question, basically. Is like, if I run a local controller that views geometry in this local fashion, can I see a solution or can I not? And so I think, fundamentally, I would say there are problems from the perspective of control that we can think about locally. Right? I need to touch this wall or not touch this wall. I think a local algorithm can actually solve that quite effectively. Do I need to walk around to the other side of the podium? I don't think that's a local question. And I think that fundamentally is a more hybrid question. So the way we've been thinking about this is to ask ourselves, like, what space should we be reasoning over the hybrid aspects of the problem? People have looked at essentially sampling into contact modes. And I think that's not a particularly useful way to reason about this because there's so many modes and so many mode sequences. So our first approach here is to reason more about sampling into the state space or position space. So for the perspective of manipulation, if I want to think about manipulating an object, pushing an object toward myself, I can think about, well, what happens if I move my arm to the other side? And then run local control. So leverage local control to make these sort of nearby mode decisions, but have some global, higher level, bi-level supervision that's allowing you to reason about possible bulk motions.
All right, I have a question. So I think the key idea here, and you said this, is choosing the right biases for training your models, right? And in this particular talk, the biases come from some physics interpretation of how contact is made and how we before all the learning revolution stuff, we started modeling contact with this complementarity constraints. I'm curious how this can apply. I mean, maybe this is not something you've thought of, but are you pushing towards choosing the right biases in other areas besides just contact? And maybe this is just a chance to talk more about locomotion. I don't know.
I would say, I think, without the locomotion side for a second, I think the same principles really should apply if whatever you're trying to learn is stiff or is multimodal. I think the same challenges occur in reinforcement learning, and the same challenges occur in imitation learning, even if that structure is not explicitly contact, but it is some degree of stiffness or multimodality. We're trying to show that. We haven't quite done it. We just started a couple weeks ago trying to show that, and for things like diffusion policies. So we'll see where that gets to. Locomotion is, yeah, I mean, it is also multimodal in the same way that manipulation is, but I think it exposes some different set of challenges. The dynamics tend to be faster, the impacts tend to be larger, the number of modes tends to be fewer. So I think certainly some of the questions you have to ask, which is for the jumping, how do we handle impacts, right? How do we handle that mode event? That's a really important question for something like jumping. Some of the same principles apply, but I haven't quite thought about how the learning bit would fit in there. So I don't know, it's a sort of partial answer, I guess, to your question.
All right, I think that wraps everything up. So thank you all for